Okay, so before we do the project, I said we're gonna have a project in this class, and it's gonna be a tall building project on ETAS. But before we start the project, I want to introduce the lateral load resisting system. Are you guys familiar with any lateral load resisting system that is being used for design tall buildings? We have talked about shear walls, right? We use shear walls to resist the earthquake and winds, right? But there is other systems out there that can be used to resist lateral loads. Sometimes there's buildings are designed like the framing action between the beams and columns to resist the lateral loads. So, and there's the shear walls, there's outriggers, there's frame to tube structure. So we are gonna go one by one and see how's each system working. But what we have been navigating over the last few lectures is the gravity load resisting systems. So we have done, like we talked about flat slab. Do you guys remember when the columns, it just, the slab resting on the columns directly? We talked about the beam, the solid slab, when the slab resting on beams and beams transfer to columns, that's called solid slab system. There is waffle slabs, ribbed slabs. All these are called gravity load resisting system. But when you have, gravity is going this way, but when you have a lateral load, so that means there's other system that can resist the lateral load. So if you are pushing the building this way, it doesn't matter what is the slab system that you have. Like, it doesn't matter much. It matters a little bit, but it doesn't matter much if it's a solid slab, flat slab. Well, they are all masses. They are all loads on the structure, okay? Okay, so what we are going to do right now is to see what is lateral load resisting systems that are out there. Okay, so first, as I told you, we're gonna go a little bit about historical background about tall buildings, and then the lateral load resisting systems, what is the different systems out there, how to choose the most appropriate system for your structure, and then we're gonna conclude with the project remarks. So in the 1885, William Lateral introduced the steel columns, and he was able to make a 10-story steel building that is in the 80s. And then the use of steel construction. So it started by steel, not concrete. And then the steel construction materials has been used. And then the thing is, when the tall buildings start, the thing is, if you have a 60-story building and you don't have elevators, that's like never gonna happen. Like, nobody's gonna go on the stairs for 60-story to live. So the limitation not only in the science of building tall buildings, but how can I get to the 60-story? So when the elevator techniques has been gotten be more advanced, more like tall buildings start to show up. So the use of steel construction materials and the development of elevator technologies make it like remove the height boundaries, like you start to go to 60 stories, 80 stories. Then in the 1930s, like there was a building in Manhattan. This building, as you can see, it's a 60-story building, was one of the tallest building at that time. In the beginning of the 20s, there was like, as you see, like in Dubai. How did we know Dubai? It's about Burj Khalifa, right? Burj Khalifa is the tallest building. Everyone is starting to know about Dubai. Everyone wants to go there because there's one remark there, the tall building that they have. So it starts to be like an advertisement material, like this is how you make a propaganda for your country. So more brands like Chrysler and car brands, they wanted to have tall buildings so that they can get known much better. So more buildings has been built, like Chrysler building, 77 stories, wall tower buildings. And then after World War II, more buildings start to come up. And as you all know, maybe you have seen some of these buildings. These are the tallest buildings in the world. There's one that is under construction since 2008 in Saudi Arabia. This building, the construction stopped for a while, but I believe the construction is back. So when it's done, it's gonna be a 1 kilometer height, 1,000 meter height. Okay, so let's talk about lateral load resisting systems. So as a structural engineer, you need to choose the most efficient system. And when I say the most efficient system, what does it mean? Like, how we can describe efficiency? Like, when I say efficient system, that means the less cost and at the same time we don't compromise the safety and the functionality of the building, right? So how we can measure that? So usually we measure that by the weight per unit per meter square or per unit area, like how much weight of the structure you have per square area. Oh, I was able to have this by this, but if you make it less, that means less cost, less labor, so it's gonna be much less money, okay? All right, so however, at sometimes the ideal design conditions are really present. Why? The architecture like want to use this system or having this crazy idea, so you have to compromise a little bit of the cost, but you tell him if we're gonna do it that way, it's gonna cost this much. Do you want to do this? And then it's not his decision alone, so you have to get back to the owner for more cost, okay? So yeah, and then as I told you, the efficiency of the structural system is compared by the weight per unit floor area, okay? So that's how we do it. So let's talk about the verse system that we have here. The verse system to resist the lateral loads is the rigid frames. So you will tell me, so you want to tell me the columns with the beams can resist lateral loads? Yeah, they can. Definitely they can, but they will be more resistance to lateral load if you design the column beam connection in a way that it can resist moment. So when you push your building, this connection want to open. If you design it in a specific way, it's going to take more moment. That means it can resist the lateral loads more. Okay, so the lateral stiffness of the rigid frame depends on the bending stiffness of the columns and the girders and the connection. So it depends on the lateral stiffness of the column, the beam, and the connection between them. So this is an example of a frame system. This is a simple frame system. You have the columns like here. Let's work. All right, so if you have like the columns here, and this is the slab system. When it gets a lateral load, what is going to happen if you have a lateral load like this? All the system is going to be pushed that way. But look at the slope of the building. So the slope of the building is very, very steep at the lower floors. But when it comes to the upper floors, it's going to get less steeper because the curve of the building is that way. So the slope at the support is much higher, but here it gets better. So the less the slope, the better the system. Why? Because when we design these columns, so the column in story number 1 here and story number 2 here, that means that there is a bending moment on this column that way. The more the deformation, the more the bending moment. But let's say this column moved from here to here as a pure translation. That means this column doesn't have any bending moment because the differential displacement between this story and this story is 0, so that means there is no bending moment. So the bending moment at the lower story is less from the upper story. So that means that this system is very, very efficient in the upper stories, but less efficient in the lower stories because the lower stories has, we call it inter-story drift. The inter-story drift between this floor and this floor. Okay, this is how we measure the performance of the floor, okay? So the more inter-story drift, the more internal forces and the more steel and construction materials, the more money, okay? So the conclusion is this system is good in the upper floors, not good in the lower floors. So sometimes we include the infilled frames. So definitely if we have a building, especially in Middle East, we put, like we don't use like much dry, like, I don't know, like the cladding or something. So you put masonry around the building, and you include this masonry with the framing action to resist the lateral load. Like for example, if you have this connection and this wanna make that way, if you included the masonry, the brick walls that you have here, the brick walls are gonna act like a tie, tension compression. So it's not gonna allow this displacement to happen, or it's gonna restrain this displacement. So infilled frames also help in lateral load resisting system, okay? All right, so that's about the infilled frames. And this is the best system ever that you can use to resist lateral loads, shear walls. And it's usually used in most of the buildings around the world. like even Burj Khalifa, it's all shear walls. This is the system that can decrease the displacement, that can make the building more rigid, that can absorb the lateral load. Okay, so shear walls are primarily lateral load, the primary lateral load resistance system. Even if you have frames inside your building, shear walls is taking most of the lateral loads or absorbing most of the lateral loads. So shear walls act as a vertical cantilevers because they are fixed at the base and then they are free all over the length of the building. And shear walls are a very good system and economical up to 55 stories. However, we use them up to like 90 stories or 100 stories because they are the best systems. Even it's gonna cost more, but it's the best systems. And why? Because sometimes other systems that are cost effective, they can't be used because architectural restraints, okay? All right, when shear walls are combined with frames, the wall attract all the lateral loads and the frame is designed only for gravity. That's what happened. If you have shear walls, we designed that all the lateral loads are gonna be absorbed by the shear walls and the frames, columns only take the gravity loads. All right, so this is actually a picture from the internet for the structural system of Burj Khalifa. If you see, all these are shear walls. Can you imagine how many shear walls? All the spaces has shear walls everywhere, from bottom to top. Okay, so this is how the shear walls, let's look at the deformed shape of the shear wall. It's like a cantilever. Do you guys remember the deflected shape of the cantilever? How much is the theta here? Zero, right? If you have a fixation, the slope is zero, okay? Then it's bent like this. Look at this. Where is the inter-story drift is much more? Down or up? Up, right? So shear walls are a very and the best system down here. Like all the stories down, they're basically not moving. They are fixed to the ground. But when you go up, they start to move. So shear walls are the best, or they are good in the lower stories, but they are not that good in the top stories. All right, so how about if you imagine if we combine frames, very, very strong frames with shear walls, they are gonna take the good from each other. So the frame is good in the top and not good in the bottom, the shear wall is good in the bottom, and you combine them together, it's gonna be much better. They are going to enhance each other. So that's a system that has a shear wall connected with a frame system. If you want to make this system much better, like you want to enhance it, like you want to then both of them, they resist the lateral loads and transfer the loads to each other, we need to enhance this connection between the shear wall and the frame system. So sometimes we make something called punched girder, like something like this. If you make a zoom in view and you make the cross section much bigger, so you enhance the connection between both systems. All right, so that's actually very, very interesting systems. Let's get more into more interesting systems. There is a system, it's called Outrigger system. Have you guys heard about this system? So the Outrigger system is something innovative. It's not a separate system. Actually, you have to have shear walls and you have to have another special system inside your building. So it's something that you can add to your system to enhance the lateral load resisting of your building. So I'm gonna draw it on the board. Okay, so let's say that this is your building. And you are an engineer, and then there's a lot of earthquakes are gonna happen, and you design seismic, and you figured out that you are gonna use a shear wall system here. But even with a shear wall, like all this is a shear wall from the base until the top, okay? And you put columns and everything, like there's actually the columns that take the vertical load, and this is the stories. Here, like this is story 1, story 2, 3, 4, 5, up to, I don't know, 100, okay? And the thing is, you design the building and everything, but there's a huge drift happen to the building. You have a 60-story and the drift is like 0.5 meter or 1 meter, and you want to decrease this drift and decrease the forces. So what we do, we come at some stories and we make something called outrigger. Like an outrigger is a deep beam with the height of the story. Like you come with this, like this is a wall, like drywall or something. but you make a concrete beam with a special reinforcement from this column to this column. Can you imagine if you have the length of your old building is 60 meter, you make a 60 meter length beam from the first column to the last column, and it has to be connected with the shear wall. And it needs to be connected with this column at the end, all the columns that it needs. And basically this system works like this. This is the outrigger, which is the deep beam, and this is the base. And you have a column, for example, at the end, and column at the start. So when this building get hit with an earthquake, whatever this earthquake look like, let's say this is the acceleration of the ground, so there's a base forces hitting the base to shake the building. So this building want to turn that way. There's a bending moment, like all the masses want to be thrown that way. So there's a bending moment on this shear wall. Like if you look at the stresses of the shear wall, there's a lot of tension here, there's a lot of compression here, and this is the stress down there. The thing is, this is gonna work as a tie, like it's gonna tie the building from the top, like you are having a strap and pulling the building, and this is gonna have a tension, like this is gonna pull this down, and this is gonna like resist that way, like compression. Okay, so this is gonna act as a tie and pulling the building in the other direction. So it's gonna make it like this. So it's gonna resist this bending moment. So there's an extra bending moment that happens. I'm looking at the action, not the reaction. Okay, if you wanted the reaction, if the earthquake is hitting that way, the reaction of the shear wall is gonna be that way, and the reaction of the tie is gonna be that way. So the outrigger induce more resistance to bending moment and more resistance to the drift. Why? Because the tie action. So let's say this building doesn't have this outrigger on the top, like this cap on the top. The reaction in this column is going to be very, very small, all the columns. But once you put the outrigger, the columns are going to absorb more bending moment. So what we did is we reduced the bending moment on the shear wall, or the shear wall can take bending moment, but we add more resistance by making the columns take more forces from the earthquake. Like let's say that the earthquake is gonna hit with a force, I don't know, 100 ton, okay, and make a huge bending moment here. So rather than having just the shear wall resisting this bending moment, we are making all the columns that are connected here to resist the bending moment. But the columns at the start and the end, they take most of the bending moment. How? Because if you have a column here, the stresses is something like this. So, right? So if you get to the neutral point here, if you have a column here in the middle, it's gonna have 0 or something. But the way that you go away, the more that you can take more stresses. So this is how the outrigger works. So let's see how it's look like. It's something like this. This is outrigger in the X direction, and this is outrigger in the Y direction. And by the way, the outrigger, you can make them multiple of them. Like sometimes one of them is not enough, so you need to have one here and one here and one there, okay? But they work better if there is shear wall holding them in the middle, okay? But it's okay to put them and connect them with columns, all of them as columns. So what is like the options that you have? So let's say you have 2 shear walls. Here, what happened? He put an outrigger here and outrigger here, and make a build of outriggers around them. So the outrigger is the one that is inside that connect the shear wall with the columns, and the one on the perimeter, we call it a build. Okay, so it's something like this. Sometimes we put it in multiple stories. Sometimes we put it at 1/3 and 2/3 and in the top, and sometimes you only need 2 at the 2/3 and the 1. So there is an optimum location of the outrigger, and this is going to be part of the project. Some of the groups are going to have to try different outriggers location and see how this is going to impact the forces. So yeah, this is, and sometimes we make the outrigger if you have a steel system from trusses. Like you make a truss system here that make the columns acting as a counter bending moment. So there's different ways that you can do the outriggers, and see how's the bending moment look like. This is a building and you have an outrigger here, and this is like you are holding the building with a tie the other side. Okay, so I believe that's almost everything about the outrigger, so we can add it to the shear wall. So let's go to the next system. There's a system, it's called the frame-the-tube system. What is the frame-the-tube system is? It's a little bit complicated. I'm not sure if we have time for it, but I'm gonna do my best. So the frame-the-tube system doesn't include shear wall. Oh, you'll tell me I can't build a 70-story or 100-story building without a shear wall? Yeah, you can. The way it works is, it's a shear wall and not a shear wall. It's something like the frame-the-tube system. How it works, you make a very, very close columns. Like, let's say that you have a building layout 60 meter by 60 meter. And you are gonna put a very, very strong column at a very low spacing. Like you have a column maybe 1 meter by 1 meter, and you come after 2 meter, you make the same column. And another one, the same column. You will see a lot of columns close to each other with very close spacing. And they are connected with a very, very strong beams in between them. Like the beams between them is very, very strong. So the whole perimeter of the building is gonna feel like a shear wall that has some holes. Like when you look at this building at the end, let's say columns here, here, here. This building, when you look at the side view, it's gonna be something like this, just like a shear wall, the whole front of the building, and has some holes for the windows. That's it. So we call it as a perforated shear wall, like shear walls that has a bunch of holes. So somehow we are trying to make this building, the whole perimeter of the building, like not only a shear wall that is 3 meter, 60 meter shear wall, and 60 meter shear wall. So the whole building is gonna act as a shear wall. So if this building got an earthquake, like let's say it got a hit with a force like this building wanna bend that way. So all the columns here are gonna have like, the stress is gonna be something like this. All this is gonna have tension, and then they're gonna go have compression, right? So all these columns is gonna act like this, and this is gonna have tension, 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 and he's almost zero, and here's gonna have compression, 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 compression. So the stresses are gonna be something like this. So basically the columns are acting as a shear wall, but there's only one downside of the shear wall. It's not solid shear wall. So it's not perfect shear wall. So there's a phenomenon happens in the frame-the-tube system. Actually, it's called the tube system, frame-the-tube system. It's called shear lag. So if this, like let's say a force hit that way, so we are saying that this is acting as a shear wall. If this is a really shear wall, the stress curve is gonna be something like this, a line, and this line is uniform until it comes here, something like this. But if this is not solid and has holes, voids like this doesn't be like that. Something is gonna happen, which is the strains are gonna be something like this, like this. So if it's a shear wall, it acts with a very, very good efficiency. But if it's a perforated shear wall or columns connected with beams, you lose all these resistance. And why this has happened? Imagine this as like this beams. Actually what happened, this beams, like the beam that is here, is connecting all these columns together, right? So basically this beam wanna move, like when an earthquake happened, this column go, so this beam wanna move. So basically it's like you have a chain, like if you have a wire or something. Yeah, like this thing. So that's the beam, right? And it's connected by columns at separate point. So when it's wanna move or wanna make like a tension compression, it makes like a curve, something like this. You are pulling column by column. But if this beam is very stiff, the beam that connecting this column is like the story height. Like this beam depth, let's say if it's 1 meter. Yeah, it's good. If it's 2 meter, it's much better. What if it's the story height? So that's actually a shear wall, right? So this beam are gonna like move as a one piece. But if it's not stiff enough, it's gonna have like a little bit of deflection. So that's actually what happened. So it pulled this column, so you are losing this. So for the frame to tube structure, the best is to decrease the shear lag. Like you are making the structure more economical. Or what I mean by more economical is that you are making it more efficient and decrease this shear lag. How can I decrease this shear lag? Tell me some options, how to make this as a shear lag. So to decrease the shear lag, I want to bring this system to be stiff enough, like that feels like as a full shear wall, solid shear wall, right? Do you guys know how can I do that? What things that I can add to my system that can make this less, the shear lag less? I mean, what can I do to make the frame to tube system feel as a shear wall?
Cross bracing.
What is that?
Cross bracing.
If you make bracing, but you are gonna close the windows, it's gonna go with the architecture. You can make the columns closer. So if the columns are closer, if the distance are 0, that means like you are becoming a shear wall. But if it's bigger, the frame to tube system is gonna be less efficient. So it's not gonna make the shear wall action. So, or increase the beam depth. Increasing the beam depths are gonna make it more efficient. So that's things that we're gonna try in the project. What if we increase the column dimension, not the spacing? So you can increase the column dimension, increase the column spacing, the beam dimension, so we can play with all that. The beam widths can help a little bit, but not much. Mostly the beam depth that helps with this. So that's about the frame to tube structure. So I'm gonna stop here right now, but next time I'm gonna tell you about other two systems related to the frame to tube structure. But I believe this is good for now. So I'm gonna share this presentation, go through the different load resisting system, and once I'm finished them, I'm gonna introduce you to the project. So, all right, see you guys next time.
Is it okay to download ETABS at this point?
Maybe you wait a little bit. Yeah, next week.